We've been talking about discrete time signals and discrete time systems. And we've talked about them in 1D and we've talked about them in 2D. And of course, there's a generalization to 3 and above. And we started with this seemingly trivial representation where we took a discrete time signal or a discrete time image and we represented it as a sum of scaled and shifted unit impulses, either signals or images. And it seemed really trivial at the time and unnecessarily burdensome. But when we started talking about linear time invariant systems, by putting in that representation of a signal or an image in terms of the unit impulse, we saw that beautiful convolution sum come out. So that representation really matters. And we're going to talk a little bit more about representation because it's going to lead to another very powerful concept in signal and image processing. So let me remind you where we were in terms of the representation. We have a signal, f of x. Again, square brackets are going to represent discretely sampled signals. And it's just a series of numbers. Here, 1, 2, 4, 5, 3, 0, 7, whatever, some length. And of course, if this was an image, then I would have a number of different rows corresponding to each row of the image. And remember that we said that we can represent this signal right here as a sum of scaled, there's the scaling, 1, 2, 4, 7, which of course are just the values of the signal, and shifted impulses. So here are the shifted impulses that you see here. So in the first one, the one's in the zero, in the first position, 0 everywhere else. I shifted it over 1, 0 everywhere else, and so on and so forth. And again, it seems sort of trivial to have done that, but again, we saw that very nice, powerful concept emerge just by simply being explicit about the representation. Of course, we call this a basis. And in some ways, it's implicit. When I tell you the number 23, you don't ask me, well, what base? It's implicit that we are talking about base 10. When I give you a signal like this, or a vector in a two-dimensional space, or in this case, a higher dimensional space, you don't ask me, well, with respect to what basis? It is assumed it is the so-called canonical basis, which is what this is right here. Nevertheless, writing it out is important because it reminds us that we've made a choice. We've made a choice to represent numbers in base 10, not base 12. We've made a choice to represent signals and images in terms of the impulses or the canonical basis. Let me now write out the algebra for this because we're going to want to look at these equations again. We've already seen this, but it's a good reminder. So I'm going to write f of x as a sum from k equals 0 to n minus 1. So I've indexed the signal on 0, and it's of length m, of a sub k, that's the scale factor that you see here in blue, times a basis vector. So notice what b of x is. Strictly speaking, by the way, I should have put that in square brackets, not in round brackets. But notice that b sub k is the unit impulse shifted in varying degrees. Okay? And I've just scaled those by a sub k. So in some ways, this is a statement. It's a statement that says a discrete time signal can be represented as a sum of scaled unit impulses. And then, of course, the question is, well, by how much? Okay? And in this case, the answer is, well, almost trivial. It's just the dot product between the signal and the basis vector. So let's make sure we understand what it's doing. So notice here now, this is the, if you will, representation, and this tells you what is the a sub k. So I give you some signal, I give you some basis, and I ask you what is the representation of the signal with respect to this basis. Think, I give you a number in base 10, and I ask you what is that number in base 12, in base 2, in base 16. It's the same game here. And in this case, with the canonical basis, the answer is very simple. It's just take a dot product between the signal and each basis vector. Let's make sure we understand that. Take your signal up here and take a dot product, please, with the unit impulse with the one in the first position. So what does the dot product mean? You line up the signals, you do a pointwise multiplication, and you sum. So when I do that between the signal and the one, that one grabs the first element and everything else gets zeroed out. Now, when I take a dot product with the signal and the second basis vector, the one in the second position grabs the 2, everything else gets zeroed out. And you can see all I'm doing by doing that dot product is zeroing out all the elements except the element that I want. And again, it seems so unbelievably trivial and overburdensome to go to all this trouble to sort of state the obvious. But of course, that basis is not the only basis, and we're going to be talking about different bases, and that's why this machinery that I've just done here is important. Now, one thing I really like to do is to think about things in signal processing and image processing and computer vision in many different ways. The algebraic way, right here, the sort of geometric picture here, and then the linear algebraic picture is often very powerful, in particular because it brings all the power of linear algebra and because it tends to generalize very nicely to higher dimensions. So let's talk about the linear algebraic picture of this story right here. So what am I saying here is I'm essentially, if you think about these equations right here, I can rewrite them in matrix form. So let's just go ahead and do that. So let's take the first equation right here, and I'm going to now represent my signal as a vector. And that's sort of what I've done over here anyway. So it's actually not that different. I've just explicitly written out it as a vector. And that, I am saying, can be written as the product of this matrix right here, which just has the basis in the columns and the corresponding weights. Okay, sure, that makes sense. Let's make sure what's happening here. This a sub 0 is going to multiply every element of b sub 0. A sub 1 will multiply every element of b sub 1. Just work out the matrix algebra and you'll see that. And so f sub 0 is then simply a dot product between the kth element of A and the corresponding basis. So that's just the matrix picture of that equation right here. Now, there's something really interesting about this basis. These basis vectors are orthonormal. And what that means is that each vector has unit length, and the dot product between each two vectors is 0. So first of all, we should be able to convince ourselves these all have unit length. Of course they do. They have a 1 in one position and 0 everywhere else. You should also be able to convince yourself that if I take a dot product between that basis and that basis, it's 0 because there is no overlap between the one values. And that orthonormal basis is very, very powerful, in part because the inverse of this matrix here is simply the transpose of the matrix. That's reason number one, and there's some more reasons that we'll see in a little bit. So if that's true, if the inverse is equal to the transpose, well then we should be able to derive this second equation here pretty easily. Why? Well, over here we have f on this side, we have our basis vector here, and we have the a's here. That's representing this equation right here. How do we represent this equation? Well, I just want to inverse this and solve for a. Well, okay, this is a square matrix over here. It's orthonormal, so it's invertible, and in fact the inverse is the transpose, so let's go ahead and compute that. Okay, so now a sub 0 is equal to b transpose times f. And now what have I done? I've said that the 0th element of A is a dot product between the 0th basis vector and what? The signal. Sure, that's exactly what we just said it was. And then a sub 1 is a dot product between the first basis vector and the entire signal. Again, this seems like a lot of machinery just to represent a fairly obvious statement. And the reason why it's obvious is that this is a very special basis. It is the canonical basis in the way that we always think about it. So we're sort of stating the obvious, but we are behind the scenes doing this, and we should understand that because that choice of basis, while very nice and very elegant and very common, is not the only basis. We can choose to represent signals and images in terms of other bases. In the same way that I can choose to represent numbers not in base 10 but in base 2, and that is very important, for example, for building a modern day computer, because base 2 is important for representing things in terms of binary representations inside the inner workings of a computer. The same thing is going to be true with signals and with images. The choice of basis matters. How you represent things matters, and we're going to be talking next about different basis representations, and we're going to be using that machinery. So please make sure you understand the algebra, make sure you understand the linear algebra, because we're going to be building on that next.